Thank you so much for coming tonight. Thank you, Knut, for that wonderful intro, and thanks so much to Bob for putting all of these talks together. How amazing! Seriously, I've been so impressed. And he just always has an incredible amount of energy. It's amazing. So I'm going to give you a little bit of a warning. This is going to be a little technically difficult. We had some technical difficulties. There's going to be some possibly annoying mousing around. You know, just use those moments to think about the future of astronomy or the future of the end of this talk when you want to ask me some questions about astronomy. But there's some movies, and I want you to be able to see them, but it's going to require some ridiculousness. So I really like starting out with this image here. So to a certain extent, this is kind of how we think about the sky all the time, right? It looks like a big dome over our heads. It looks like the stars are painted on there. This guy is, I think, supposed to be some old school version of me and Knut and many other people in this room, the astronomer, who is trying to peer past the dome of the heavens to understand how it works and what's going on behind it. And this presents a very specific view of the night sky. One that I think is familiar, which is that we tend to think of it as kind of being static. Something that is just above us, that, you know, sure, rotates into and out of our view as the Earth itself rotates, and changes on a yearly basis as we go around the sun. But ultimately, something that, you know, could, for all practical purposes, be a bunch of things painted on the sky above us. And what I want to talk to you about tonight is that this is actually not true, and that the universe is extremely variable and is filled with change. On a variety of timescales, from, you know, nanoseconds to minutes to hours to days. And I think that this is very different than the rest of the story that you often hear with astronomy, particularly because we tend to think of like astronomy and things in space as evolving on like millions and billions of years and cosmic time and all of this sort of stuff. But actually it changes on really human timescales, and I think it's kind of compelling and interesting to think about all the stuff that's happening up there when you look at the night sky. And in particular, I'm going to talk about this because of the fact that this wonderful telescope we're all here to meet about is going to give us kind of a view into that variable or transient night sky that's above us all the time. So I wanted to start with a static image, and to talk, you know, I don't mean to brush aside the wonderful images of astronomy, right? I think one of the things that's really amazing about astronomy is that it does have this incredible power of the image. This, of course, is not taken by our future telescope. This was taken by the Hubble Space Telescope, one of these iconic images from the Hubble that you see all the time. And it's but one of these incredible images that have made it out into the public mind, really. So these have made it out, you know, not just being, you know, beautiful images, but you see them everywhere now. And it's hard to believe that these images were not always a part of our lives. For some of you who are quite young, they might have always been a part of your life. But for most of us, this started in the early 90s, early to mid 90s, when the Hubble launched and started to return these things to us. And so these things that are now our iconic images of space have actually sort of reached the pinnacle of what you could hope for science, which is that it's totally like plebeian to see these things. You know, they're just in our public consciousness all the time. And I wanted to show you, in particular, an example from, this is, I think...
Like a bluegrassy type of fun times. They're amazing. They're a new hot band. It's just going to be a great night tonight. Yeah! I'm sorry. Who said that?
I said it. Hey, man, your show is good. Matter of fact, your show is great, but you know what's greater? The exquisite interstellar photography you get with the Hubble Space Telescope. Y'all love that Hubble telescope, right? Yeah, make some noise for the Hubble Space Telescope.
Yeah. I love the Hubble Space Telescope. Wait, are you serious?
Yeah, man. When it comes to vibrant images of celestial bodies and the various celestial bodies that make up our universe, I mean, nobody's got your back like the Hubble Space Telescope. You need an image of the Orion Nebula? Hubble got you. You need an image of the galaxy cluster M0735? Hubble got you. You need an image of the massive star Via Canis Majoris. Hubble got you. Regular ass Jupiter.
All right, yeah. Hubble got me.
Hubble got you.
All right, yeah. You got your own doll. Hey, buddy, thanks for interrupting and showing us that. But you realize Hubble's just a telescope, right? It's just...
Whoa. Just a telescope? Jimmy, if Hubble's just a telescope, then how do you explain this?
Telescope. It's called Hubble. Galaxy Cluster 1. Hubble got you. A Bell 901. Hubble got you. Birth in the Eagle Nebula. Hubble got you. The remnant of Kepler Supernova. Hubble got you. The dude who sells me shawarma. Hubble got you. Business lady with the chicken pork. Hubble got you. Yo, the tourist from Peru. Hubble got you. A homeless dude with a kazoo. Hubble got you. A rat. Holla that squirrel. Hubble got you. Yo, everyone in the world. Hubble got you. Yeah, this is chapter 1 in my 97 chapter epic poem to the Hubble Space Telescope. HST. Unlike any other, you are my brother. Forever telescopic, so don't change the topic. Double Hubble? Now that'll be trouble. Stars burn, nebula soap bubble. I'm out. Hubble got you. Hubble got you.
That was great. That was great.
Haha, yeah. Explain that, Jimmy Fallon.
Explain it. You went out, you spent money, you made a hip-hop video about the Hubble Space Telescope.
Yeah. That's an accurate explanation.
Yeah.
Hubble got you.
See, everybody's saying it. Hubble got you.
Thank you so much. Everyone's saying it. Hubble got me indeed. We come back. Jerry Seinfeld!
Get down. Get down. Yeah.
Thank you so much for your patience. So I'm showing you this because this, I think, is probably speaks the most, aside from the fact that the Hubble Space Telescope has like a special character devoted to it on the Jimmy Fallon show. You see this kind of clothing kind of around all the time, right? These are Hubble images, for the most part. Sometimes when you see clothing with this like galaxy print, it's just artist conceptions, but more often than not, it's actual Hubble images. And that's significant for a variety of reasons. For the most part, it's significant because it's actually, you know, space, and it's something that's thought of as a pattern on a piece of clothing because it's so commonplace. But it's also significant because it's public data. So the reason that these prints can appear on a piece of fabric that you can buy at like Journeys in the mall is because that data is public. It belongs to you. It belongs to you because you paid for it. Your taxpayer dollars pay for things like the Hubble Space Telescope. And they do things like fund science and future telescopes. And so the fact that this can appear is because this data is public, and I think that's really significant. So, you know, we started with our astronomer as the person who's viewing the static universe above him. And I think this is a tendency for us to all think of the universe this way, as I said. But what I think is really exciting about this next decade and a half leading up to, you know, the completion of the actual building of the Large Synoptic Survey Telescope and its eventual deployment, is that what we'll share in the coming decade is not these static images. As beautiful as they are, the LSST serves a different purpose, which is revealing the variable night sky to us. And that's significant because of the way that movies have changed the way that we think about the world around us. So, you know, I've made this big point about static images being important. It's not to say that we didn't know that the universe was changeable from, you know, a long time ago. So what I'm showing you here is two different versions of the changeable universe from science and from art. The first of these on the right, of course, is Van Gogh's Starry Night. And I think that this is, again, another iconic image that you can buy on a mouse pad. But it shows you the sort of motion inherent to the night sky, probably something that we're all familiar with on a night where we're out and it's dark and there's twinkling stars above us. Now on the left here is actually a page from Galileo's Notebook. And what you're seeing are his notes on the motion of the Galilean moons, which at the time, of course, were not yet called the Galilean moons. These are the 4 closest moons of Jupiter. And what you see is him drawing the position of where he sees the little satellites moving. Those little asterisks are the moons of Jupiter around the circle. And so the idea that things were moving in the heavens and changing is not a new one, but we're about to kind of blow the lid right off of it. And we're going to go from being able to share in changeable night sky experiences that we can see with our naked eye. So for example, here are the auroras. This is also a video, but we're not going to go through the whole thing because there's no joke in this video. So the aurora, of course, which you can even take a cruise to go see. Things like meteor showers. Those are shared experiences that we have of changeability in space. And the fact of the matter is that we come together in moments like that because it allows us to share in something that evolves on a human timescale. But also for astronomers, the thing is that you can only learn so much from a static image. Now don't get me wrong, those Hubble images are very information rich. All those beautiful colors that make them appealing to put onto a piece of clothing are actually encoding physical information. And in addition to the fact that that data is public, I always look at like those t-shirts and dresses and stuff, and I think about the poor other version of me, like the astronomer that stayed up like several nights in a row to write the proposal that allowed them to use the Hubble Space Telescope to take that image so that it eventually could appear on a shirt that you could buy in Turkeys in the mall. Now they're very information rich, but ultimately the information that you get from a static image is limited. You could take something like this. Is the cake smashed because the dance party at the wedding reception was really awesome, or because the bride ran out the door? I don't even know what this is. What happened here? You get this isolated moment in time that doesn't actually capture all of the information that's happening above you. And it serves us to remember that we learned a lot about the world around us by the advent of movies. So these are photographs taken by Muybridge. This was back when we weren't actually sure whether horses left the ground when they galloped. And now, we know that. And we know that because of taking not just a single image, but many images over time. So this is an artist's conception of what the LSST, the Large Synoptic Survey Telescope, will eventually look like. The thing you're seeing here is not, of course, the telescope itself, but its main control center. So there's that sort of futuristic Bond villain-looking layer underneath it, where I promise no evil will happen. It is just probably going to be a bunch of computers. And then the sort of slotted thing on the side is what we call the dome, which in modern astronomy doesn't often look very dome-like, but that's where the telescope lives itself. And it bears remembering that the era of astronomy that we're in now, and that LSST will be taking part in, that will sort of amplify, take to the next level, is actually very different. Probably when I showed you that image, that is perhaps not what you have in mind when you think of telescope. Probably you have something a little more like Edwin Hubble up here, looking in this sort of long conical, well, long tubular thing, cylindrical thing. He's staring into the eyepiece, he's smoking a pipe. Well, much like we don't smoke at the observatory anymore, we also don't typically look in the eyepiece. Actually, most of observational astronomy now does not actually involve looking in the eyepiece of the telescope. Usually you access the information from the telescope in the form of digital images, and I'll talk a little bit more about that momentarily. But also, we're moving away from the time where people observe single objects over and over again. And instead, what we're getting to is what we call survey astronomy. So this is where instead of just looking at a single thing or a couple of things over the course of the night, you actually use a telescope to kind of robotically map out the sky above you. And so this is you can think of it as, it's a little diminishing to call it the precursor to LSST because it's actually a huge accomplishment in and of itself. This is the telescope for the Sloan Digital Sky Survey. This lives in New Mexico. It looks like a flower, kind of, but there's actually a telescope in there. Works pretty similarly to LSST, and at the very end, if we feel like messing with the controls again, I'll show you a video of it operating over the course of the night. And essentially what it does is map out the night sky, and it took roughly on the order of a decade to do this once, for the most part once. And what it did was create a huge database of all of the things that it observed, whether it be galaxies or stars, things within our own Milky Way galaxy, our nearby galactic neighbors, or things just beyond and well into the deep universe, things that allowed us to trace out the structure of the universe itself. And while a giant database full of information doesn't sound nearly as exciting as being at the telescope with your eyepiece and your pipe, it is to astronomers in particular because it represents this wealth of data, this giant treasure trove in which we have hidden the secrets of the universe. And the significant thing about LSST is that rather than going through just this entire night sky over roughly a decade, it's actually going to image the entire night sky roughly every 3 to 5 nights for 10 years. So think about that for a moment. So now you can see the comparison that I was making at the beginning of the talk with having static images versus movies. Essentially what LSST is going to do is make the longest stop-motion cosmic movie ever made, essentially, and certainly the largest over the entire night sky. Now it'll be a little bit different than the Sloan Digital Sky Survey, which, as I told you, the telescope lives in New Mexico. We're going to be building this down in Chile, right about there. There is a sort of a picture of where it will sit on the ridge of this wonderful mountain. We actually just started construction this year, so we had what we call the first stone, which is like a great celebration of the beginning of construction in Chile. And there's even, you can Google LSST webcam and watch what looks exactly like a construction site, but on a mountain. But we'll eventually have a telescope in it, so if you have labored like I have for many years without actually seeing a physical telescope, it's kind of cool to be like, oh, it's going to be there, So when this is built, it will be operating for these 10 years, and all of the data will be publicly accessible by the US and Chilean communities, and with our, we have some international partners as well. And so this links back also to the importance of public data. So those of you who are small in the audience now, if you decide that you like astronomy, this means that this data will be waiting for you in a couple of years. And I think that's really exciting because it means that you can actually use it. If you're a teacher, you could use it in your classroom. If you're an amateur astronomer who right now enjoys looking through their eyepiece, you can also augment that with this. And I'll talk at the very end about citizen science, where you can participate in learning about some of this stuff via the web. Now, this is probably also not what you think of when you think of a telescope. This is our model telescope. You can see we have aliens that work on it, but there's your humans for your scale. They're not really aliens. Trust me, I'd be really excited if we found aliens on the LSST construction site. You can see why we were joking about calling it the Large Slightly Stubby Telescope, because it has this sort of squat appearance to it. And this mirror here is quite big. It's like 8 meters. And this telescope is capable of slewing in a matter of seconds. Slewing means just moving to different spots in the sky. And so it's essentially a very, very fast light bucket that's able to map out the entire night sky over and over and over again with very little downtime. And so, not only will this not be an era of astronomy where we're all looking through the eyepiece, this will probably be an era of astronomy where we're not allowed in the dome because it might actually be dangerous to get hit by the telescope. And we are a very safe project. This is one of the things that I have learned this week. So what LSST really is, aside from just being a facility, is it's not just a telescope, it's how we use it, right? I mean, we could use LSST to take one picture of the sky and then stop, but why would we do that? Instead, what we're going to do is take our 10 years to make a survey of 37 billion objects, where objects just means stars, galaxies, whatever it happens to be, in space and in time. So not only will we look across the whole sky and out into deep space, but we'll do it again and again, and we'll be able to see how things change. Now, we have these sort of 4 different areas, and if you've, how many people have gone to more than one of these talks this week? Okay, so like half the audience or so. So you'll probably notice that some of these themes, like the dark universe, solar system inventory, mapping the Milky Way, have been captured by some of the speakers that happened earlier this week. And I think these were filmed. Is that correct, Bob?
Yes, they were.
Yeah, so you can, yes, right over there, as is currently happening. So if you're interested in hearing about some of these other scientific goals that LSST is going to look into, and you're like, man, I really wish that I came last night to learn about the dark universe, you can actually do that. You can go online, and I'm sure Bob will be happy to help you figure out how to do that. So I'm going to talk about the transient universe, which sounds sort of weird, but transient just means something that changes in the night sky and that never recurs. But I wanted to talk a little bit about how a big project like this actually works. You know, I think because we have this image of people being at the telescope looking through the eyepiece, it being very solitary, like, what's the adjective that comes to mind when somebody says scientist? Put a word before that, shout it out. Cool. Okay, I heard cool. I also heard Frankenstein. I appreciate whoever yelled cool, but I appreciate whoever said cool, but Frankenstein is more common, unfortunately. So there's this idea that we're like the mad scientist, right? That we're laboring alone in lab coats and we're on the mountain by ourselves. And actually, what astronomy and science in general is about is a lot of cooperation and a lot of collaboration. It's actually a field where you spend a lot of time working with other people, and they're often other people that you might not have picked to be your friend. I mean, maybe you would have, but you're united in the fact that you want to figure out these things about the universe. You have this common goal. And so really what makes LSST tick is not that it will map out the night sky. Like it's technologically incredibly impressive, but it actually, I think, is just as impressive that hundreds of people can get together and make this happen. And so I wanted to show you some of my colleagues. This is from last year where we were in Phoenix instead of lovely Bremerton. It was a lot hotter than it is here. But this is the team. But I wanted to actually flash back a little bit further to somewhere that's closer to here. So this is in Friday Harbor, and this was in 2008. And we're sitting in the main cafeteria of the fisheries lab that's at Friday Harbor. And what we're doing is we're figuring out how we're going to convince the rest of the astronomers that the LSST is the way to go. How are we going to make our case that this is the telescope? Of all the different telescopes, one of the cool things about being an astronomer is that your colleagues have lots of really good ideas. And so, given that you have to pick one to be the top, how do you go about doing that? Well, what we did was we wrote a book. And this group of people were sort of the beginning of it. You can see I look much less tired. I'm all the way on the left. You might see some of these faces actually walking around this week. Many of these people are here in Bremerton. And what we did was we got together and we wrote the LSST science book, or all of the cool things that you can do with LSST. And it was built kind of around those science cases, the dark universe, the transient universe, mapping the Milky Way, looking for the solar system objects or comets and asteroids that might actually impact us. And what we did was we wrote out all the things that you could do with this one telescope. So if we build this one telescope, we can do all of this cool science. And that's ultimately what led to LSST becoming the flagship that it is now, and becoming this giant collaboration. It was already a pretty big collaboration of people working together to make the telescope happen. But the reason that it's being built is that we all got together around this common goal. And so I think that's really cool, and it's, to the best of my knowledge, I don't actually think other fields do exactly something similar to this. This is a part of a process called the decadal survey, which is a really boring way of saying everybody throws their opinion together. Like, it's almost analogous to if you think about, like, in fairy tales, there's always like a giant census of all the land. It's almost like the National Science Foundation is the princess, and all of the princes from all over the land are coming to argue their case. Except in this case, it was which telescope we were actually going to choose. So in the decadal survey process, everybody writes what they think the most important science question is that they can answer over the next decade and how they'll go about doing it. And that's actually how, again, we decide to spend the part of your tax money that goes towards the National Science Foundation and funding research. That's how we do it, is we all get together and we all cooperate. And this is something that I think gets lost a lot in how we talk about science. It's really not just one person laboring alone. So a little bit about the telescope itself. I've shown you sort of that slightly stubby model. But it is actually physically in existence. To give you some idea, this is the actual glass of the telescope. So this is from a couple of years ago. LSST has this really cool design where there's a main mirror part that actually has a second part of it, I'll show this momentarily, carved out of it, that you can see that dashed line has slightly different curvature to it. And then there's this glass blank that was also manufactured. And you can see that the telescope is really, really big, right? Because these are the pieces of glass that will eventually become the mirrors. And actually, just this year, we finished we finished the first and third mirror, that thing that I was saying, that dashed line will be carved out. And you can look and see that it's very, very shiny. Again, there are people in the background there. This is a tweet from our president of the Adler Planetarium, who was with me at this event, who said, "It's a good day when you need a panorama to shoot the telescope mirror." So, in other words, this is so big that it's actually difficult to capture. And so this very shiny piece of glass has now been put away extremely carefully. This blue sort of coating on it is, it's a little like when you buy a mirror in the store and there's like a little piece of plastic film over it. It's just a protection for the mirror. In part, there's a protection for the mirror because there's this crazy suction cup machine that moves the mirror around. It's really quite amazing. You can see it in action over here. And each one of those little orange things is a suction cup that looks like that. And it has to, obviously, it's very heavy, and it's very delicate because it's been polished so incredibly finely. Because that polish, right, just like you would want to reflect, you want a mirror that reflects your own face very well to be able to see it, you really want a perfectly pristine mirror to be able to capture and bounce all of the light that's coming to you from the universe into your digital camera. And so now it actually lives in a box in an airplane hangar, awaiting the building of the physical mount that will hold this mirror itself and will allow us to do all this cool astronomy with it. The mirror itself, I meant to take a picture of our new deputy director and Photoshop it in over there, but I didn't quite get to it this week. So instead you get this clip art of a 5'5" man wearing a suit. Also not an accurate depiction of a scientist. So this will be the largest digital camera ever made. And you know, this is I think a good time. I'm sure some of you are astronomers who like to observe in your backyard and are maybe familiar with this. But many people don't know that actually telescopes and astronomical cameras are really just like digital cameras with really, really fancy optics. So that mirror is responsible for bouncing the light that comes to us from the universe into what is essentially not that dissimilar from the kind of camera that you would have if you have a digital camera or a camera in your phone. Many years ago, of course, the film that was in the cameras that we all used was replaced by digital detectors. These are called CCDs. And in LSST's case, they're very, very big. So we have this wonderful picture. This is Suzanne Jacoby, one of our education leads. And she is holding, obviously not the actual detectors, but a cardboard version of them with the full moon for scale. And so this gives you some hint as to why the LSST will be able to see so much of the sky, is that even in just one image, it can take this huge fraction of the sky and take that picture and then move very quickly to get another one and another one. And this is what helps us when we do, we call it tiling the sky. This is what helps us observe so much of the night sky and to be able to do it again and again and again. So I've talked a lot about how the telescope works, both from a people standpoint and also from a technical standpoint, but I want to tell you a little bit about the actual astronomy that we expect to see. One of the things that I think is most sort of compelling for me as somebody that works on planets orbiting other stars is actually just our ability to study how stars vary in time. Of course, our galaxy itself is made up of many stars. Many of them are like the sun. Many of them are actually smaller. And I'm showing you an image here from the Solar Dynamics Observatory. And I think I will show you the video that this image originally was after this so you can appreciate it. But the Solar Dynamics Observatory has its own YouTube channel, and you should go and watch it. I do so quite frequently because I think it's really cool, but I'm kind of a nerd, so you should just go do that. Nobody has to know. So the Solar Dynamics Observatory observes our own sun, which is a sort of middle-sized, middle-aged star. It has on its surface, this image is taken in either the ultraviolet or the X-ray, I think the ultraviolet, but it has all of these surface features. So when we're kids, we all draw the sun as this sort of yellow ball. But in fact, our sun is what we call magnetically active, which means that it has a magnetic field just like a refrigerator magnet does, essentially. And what that does is it creates these sort of loopy structures that you see on the surface here, in these dark and light patches. And in addition, the sun itself spins on its axis like a top. And so as those dark patches and light patches come into and out of our view as we sit and watch it with something like a telescope, I do not advise you looking at the sun. You will A, not be able to see the variations, and also you will not be able to see anything, so don't look at the sun. Not directly. Go to the YouTube channel. That's why there's a YouTube channel. As it spins around on its axis, this makes the sun overall get darker and lighter. Now, here in our solar system, we have these wonderful front row seats to actually be able to observe our sun and its wonderful, beautiful, detailed surface. But the thing with other stars is that they're actually so far away that for the most part, there are essentially no other stars, very few, that we can see the surface of. And so one of the ways we study whether our sun is a so-called normal star is we look for these stars to get lighter and darker as the dark patches that they also have on their surface come into and out of our view. And the other side of this is that when I do play you this video, what you'll see is that planets actually also pass in front of their star, and they block a little bit of the light from getting to us. And so one of the things that we can do with any kind of telescope really that's capable of measuring how bright things are with time is to not only study the kinds of things that we see on our sun and then compare it to the other stars in the universe, but we can also look for those signatures of planets passing in front of the star and actually find other worlds orbiting other stars like and very different from our sun. And so this helps us understand our place in the universe because we're the only planet that we know that is not only habitable but inhabited. And so one of the things that we'd like to do, or at least that I'd like to do, is to be able to find life beyond our solar system. But part of that, at the moment anyway, with the technology that we have available, is understanding how typical our star is. Because all of this so-called magnetic activity, these loopy structures on the surface of our star, are responsible for showering our Earth with ultraviolet and X-ray radiation, with energetic particles that actually create the aurora that I showed you in the very beginning of the talk. And so we know that we here on Earth are impacted in various ways by what our star is doing. And that's why it's important to understand whether our star is typical or not, because that ultraviolet radiation is something that you block with sunscreen, right? X-rays are dangerous to life. That's why when you take an X-ray, you block everything that is except what you want to have X-rayed with a lead curtain, essentially. So, we want to understand whether those things are good or bad for life. And one of the easiest ways to do that is to see what they do in the visible light that's easier to observe than things like ultraviolet and X-rays. As sort of ordinary as our sun seems, it being the closest star, the other stars that you can see in the sky, one of the things that LSST will do is allow us to map out how those stars are changing. Now, oh boy, come on. Haha. So I see one of the world's experts in these objects in the audience, right back there. This is another very typical kind of thing that we see out in the universe when we go looking for objects that change. It's an artist's conception because these are all very far away, and unfortunately we don't get images like this. But this is a system where you have two stars, so it's very typical, even though our sun is a single star, it's actually quite typical for stars to live together in space. We call these binary systems. And it actually can even happen that you have triple stars or quadruple stars. But in binary systems, sometimes the stars are slightly different sizes. They're slightly different masses. And that means that they age at slightly different rates. And what can happen is that you can have a star that dies ahead of its companion star. It becomes what we call a white dwarf. This is eventually what our sun will turn into. So this white dwarf here is this object here on the left. And one of the things that can happen is you can have the star that's very red here is sort of an aging, it's very bloated. It's what we call a red giant. And this is a phase that our sun will also go through before it becomes a white dwarf. And as they start age, if one dies ahead of the other, and the other one becomes this puffed up red giant, it can actually start to sort of gruesomely cannibalize its companion star. So what you're seeing in this artist's conception is material from this red star pouring down and being funneled onto the dead remnant of its former companion. And what can happen in some cases as that material piles on and piles on and piles on is it can have what we call outbursts, where the material that's on there becomes so dense that it can actually essentially undergo burning, where you get sudden increases in the brightness of the system. And so this is another typical thing that we'll expect to see. Unfortunately, we don't get these, as I said, these beautiful pictures that we see with artist conceptions. But this is one of the cool things about being an astronomer, is that you can take something like data from the Large Synoptic Survey Telescope in the future and look at the way the brightness changes and actually learn a lot about what's going on and whether you would expect, for example, the material to pour off in this kind of disky formation that you see here, or whether you would expect it to pour down onto the poles. So astronomers are always, they might be seeing what looks like a graph to the uninitiated in a way, but we're always seeing these pictures in our minds because the imagination that you have to have in order to interpret your data is, I think, common to most astronomers. So in addition, these are examples, these previous two examples are things that are kind of close to home. They're the kinds of things that we see within our own galaxy. But one of the important things that LSST will do is to be able to actually map out the universe itself, and in what we would call a cosmological or a very distant, very big scale. And what I'm showing you here is actually a supernova that just went off a couple of years ago. It's this very bright object that arrow is pointing to in this beautiful spiral galaxy. So our Milky Way would look not terribly dissimilar from this galaxy if we could zoom and look outside of it. Unfortunately, we're always stuck looking through the veil of our own stars, but we've learned enough about mapping out the Milky Way that we know that we expect it to have this kind of structure. And actually, one of the things that LSST will do is it maps out those stars even better, is to better understand what our own galaxy would look like. But supernovae, these dying stellar explosions, these are in fact the explosions in the sky. They're in the title of this talk. These supernovae, when they go off in other galaxies, they allow us to trace out not only stellar death, but in some cases, actual distance in space. And so they're something that we call standard candles to a certain extent. One of the tricky things, of course, is that many different kinds of stars explode when they die. And one of the things that we have to be able to do is to figure out what kind of a supernova it is. Because some of them are really good for being used as what we call standard candles, which just means that we know how bright it is. One of the tricky things about looking for things in space is that you often don't know whether something appears bright or faint because it's far away or because it's intrinsically faint. And so if you know how bright something is, no matter what, for example, a 100-watt light bulb, then you can figure out how far away it is by looking at how bright it is apparently to you, whether it's your telescope or your eye. And so one of the uses of supernovae over the years has been to trace out the structure of our universe itself. The supernovae are what are responsible for our being able to figure out that the universe is in fact not just expanding but accelerating, because we were able to trace out their distances and their speeds as a function of distance in the universe. And so being able to observe these stellar explosions, to catch them as they're happening or even before they get to their peak brightness, gives us a way of telling what kind they are and if in fact they are the standard candles that we're looking for. And that in fact will help us trace out not only just the intrinsic interestingness of the way that stars die and explode, but also allow us to trace out what our universe is structured like and how it's evolving on a truly cosmological scale. Now, one of the things that I think is really cool about LSST is that because it's capable of observing the night sky over and over and over again, and out to great, great depth, very, very faint objects, we're also going to start to find some really weird things. So what I'm showing you here is an artist's conception of what's called a tidal disruption flare. So you can think of this as sort of a timeline from left to right. You have a star that has approached this artist's conception of a black hole. So black holes sort of sound very mysterious. They're probably the top thing I get asked about besides aliens. And I'm not kidding. I was totally not a joke. So black holes, the small versions anyway, are basically the leftover remnants of very massive stars, stars that are bigger than our sun. They're not really all that exotic in the sense that they're just leftover dead stellar remnants. And if you get close to one of them, you do experience some weird effects. They have a very strong gravitational field around them, essentially, just because they're made of a lot of stuff. In the same way that anything that is made of mass has a gravitational attraction to other things that are made of mass. But in the case of black holes, because gravity is very, very strong, strongly dependent on how close you are, you get what are called tidal effects, where some part of an object that's closer to the thing that's exerting that gravitational force gets pulled more strongly than the part of it that's further away. Now, in the case of this tidal disruption flare, what's happening is that essentially the star has approached the black hole too closely, and it gets shredded. So it doesn't fall into the black hole per se, but this tidal force, this change in the gravitational force from one side of the star to the other, shreds it and sends its guts across the skies. I should probably give this talk in October or something. It's very gory. Lots of stellar death, lots of stellar cannibals, guts all over the sky, but it's true. And so what happens is that we observe this flare, or this brightness change. And these are very rare. They were only been observed really over the past several years. And one of the things that we expect to see is these very rare events in LSST, because in fact, one of the things that you get when you're able to see the entire night sky and to collect all of the information that you could possibly collect is that you get things that you really don't understand. And so one of the things that I really am excited about is that I don't know what LSST's most exciting discovery will be, because at this point, it's impossible to know. And that means that, you know, again, junior scientists in the audience, this could be a discovery that you make in the future. Now, this sort of brings up an interesting lesson from history, and we'll go back to Galileo's time momentarily. But this is one of the things that, to answer this gentleman's question actually, like what are we all doing here talking to each other this whole week? One of the things that we're trying to figure out is how we will actually turn all of this amazing data that we're going to get, these observations of space, into actual discoveries and scientific knowledge. Because one of the things that you get, if you make all these measurements, you get an observation, right? Something is happening. I was observing this part of the sky and there was nothing there, and then all of a sudden there's a very bright light source, and I'm seeing it fade away. What is it? Is it a supernova? Is it a star that's flaring? We may not know. So what we do is we characterize it. We say, how is it happening? How brightly is it fading? Or how rapidly is it fading? How brightly does it shine when it's at its peak? Does it have a very unusual color? Is it very blue? Is it very red? And then what we ultimately hope to do is to turn this into understanding why it's happening. And this is a tricky thing to do, and it's in fact the process of astronomy boiled down to itself. But we're about to enter into an era when we have so much data that it's actually really difficult for us to look through as individual scientists. And there's this wonderful lesson from history that the ability to observe something is not the same thing as discovering it. So this drawing from Galileo's Notebook, again, Galileo had very messy handwriting, also not in English, so I can't read it. This is where Galileo recorded the presence of Neptune in his notebook. He thought it was background star. So in Galileo's notebook, lo these many centuries ago, is actually what could have been the discovery of Neptune, but wasn't, because he didn't realize that what he had actually observed. And so this is sort of a very small scale reminder to us that just because you see something doesn't mean you've made that discovery yet. And so one of the things that we think about is how do we actually, we call it mining the database. So we get all of these observations, all of these images, these measurements of how the universe is changing with time, and how do we actually turn it into a discovery? Because we'll see many different kinds of things, right? There's the stuff that we know is out there and that's very common, things like stars like our sun. We'll learn things about them, but we know that they're there already. And then we'll see things that are not very common, but are known, things like tidal disruption flares, the star being shredded by the black hole. And then there's the stuff that we just don't know how to look for because we haven't been able to observe it yet. Either we've never gone deep enough or phased enough to be able to see it, or it's just intrinsically very rare, or we've never been able to observe it before. It turns out it's common, but we just haven't been observing in the right way. And so, you know, if you like astronomy, but you know, perhaps there are people here with budding interest in computers. One of the things that is very important to us now is to actually be able to use computer science. So in part, a lot of what we're doing this week is talking about how computer scientists and astronomers can come together. So not only are we a collaboration of many different kinds of astronomers, we're also a collaboration of different kinds of astronomers who, some of whom come from computer science that just are interested in using computers to mine information for astronomy. So one of the things that you'll hear more and more about is something called machine learning, which sounds like the Terminator movie's premise, basically. It's not that. So this is using computers to figure out what interesting things are in your giant observations of all the things that are happening in the universe. And I like to describe it as a way of figuring out what something is like before you know exactly what it is. So let's say that you have this big collection of pet toys. Maybe you're an alien, maybe you don't know that they're pet toys. You could go and look at these things before anybody tells you what they are, and you could probably sort them based on their shapes, right? So in this particular case, you have things that are sort of circular, things that are sort of mouse-shaped. Yeah, circles and tails, right? And then things that are big at both ends and have something connecting them in the middle. Now you can sort through all of this stuff even if you don't know what these objects are, right? Because you can look at their shapes and their common characteristics. Ultimately, what you'd hope to be able to do is to figure out why they're similar to each other. But you don't actually need to know that these are cat toys, dog toys, and is that a gerbil, a hamster? Rodent toys? That sounds terrible. You don't actually need to know what the underlying physical cause of these being the way they are is, for you to be able to sort through them. And so one of the amazing things about computer science and the way that it's helping astronomy is that you can actually sort through all these amazing observations of the universe, and it actually goes looking for something that you don't know what it is yet, which I think is sort of like almost like a mental twister. So one of the things that we're hoping to find is something that we don't know to hope to find yet. Who here has a junk drawer in their kitchen? Okay, so if it's in your kitchen, it's probably full of like random utensils and then some other stuff, or maybe just truly random things, right? My like junk drawer of shame is in my desk. It is filled with pens. Filled with pens. Probably most of them don't work very well. Some of them do. Some of their pens are pencils. In addition, I really hate change. Like I never have any pockets, and I don't know what to do with it. And so I sort of like this as an analogy, is that in that drawer somewhere is something that's actually really worth something. There could be rare coins in my junk drawer, and I wouldn't know because it's mixed in with all the other stuff. But what these algorithms, these computer programmers, computer programs allow us to do is to sort through the stuff that we observe, to sort it out and to characterize it based on common characteristics, and then to look for the things that are truly rare, that don't resemble anything else that we've observed. And we're hoping that in the next decade or so that we're going to find something that we've never seen before. And so what I'd like to do is actually to enlist all of you in helping us do this. So you know, I made this point at the beginning of the talk that LSST is a very fancy telescope. Very fancy telescope with a very big mirror and a very big camera. But really, LSST is a collection of people. And you know, there's a tendency to call like scientists are like, oh, they're genius, or they're Frankensteins, or they're really, whoever called us cool and smart, thanks for that. But really, we're humans, and science itself is a human undertaking. And you don't have to be a genius to be a scientist, you just have to really like working on science stuff and pay a lot of attention to it. And so in the way that LSST now is a collection of scientists that work on how to build and deploy this telescope, the actual era where we're taking data and that data is public, that's something that you can help us with. So, and you can actually help out scientists now. So there's this project called the Zooniverse. This is a website. It's called zooniverse.org. So zoo, just like where you keep the animals, and niverse, just like universe. And you can go here. There's a whole bunch of different research projects that allow you take a little tutorial, it takes like a couple of minutes. It's very nicely designed, so I promise it's very painless. And then in a matter of minutes, you can literally be helping out with somebody's research project. So we've had a number of very successful examples of this using space data, something called Galaxy Zoo. There was also Supernova Zoo in the past. And there's all kinds of stuff like that. If like I've ruined your love of astronomy in the course of the past hour, there's also like animal projects. So hopefully that hasn't happened. I secretly love the animal projects because I think about space all day. But this is something that is called citizen science. And it's where you don't have to be a scientist by profession. You don't have to go necessarily to as much school as I did. If you want to, you should. But you can actually participate in scientific research and help out now. And you don't need any special software to do it aside from your ability to access the information via the web. So one of the things that we're really looking forward to is that as we sort through all this LSST data, we sort our pens and pencils into the ones that work and the ones that don't, and the purple ones, the yellow ones, the red ones. We need your help to be able to figure out which of those coins, that leftover buried treasure that's bound to be in there, is really valuable or not. And that's going to require a lot of eyes, people who are astronomers and also people who are not. So you should definitely keep an eye out for this. Maybe, maybe get going now, start roll those wheels up slowly so that when the survey actually starts, you can help us make these discoveries about the universe. And it's my hope really that this sort of movie era that we're moving into with astronomy will be just as binding, and this is a particularly good setting for this talk because we're all sitting in a movie theater. Watching movies, the things that human beings have created for one another to watch, has been a very bonding experience. Like it's an experience to go to the movies. And so what I'm hoping is that, in the same way that observing a night sky, or going to a meteor shower, going to a movie can be a bonding experience, I'm hoping that in the era of LSST, this will be something that bonds us together all in discovering what there is to know about the universe. So with that, I'll take questions and maybe show you some movies. Who knows? Question? You sir back there.
Doctor, what's your part in the LSST team?
Good question. I am the head of something called a science collaboration. So in LSST, there are many, many, many different roles. You can be a person that works in the physical hardware, you could be a person that works in the software, or you could be a member of the scientific community that will eventually work on LSST, and you can be part of something called a science collaboration. So what does that mean? The science collaborations are groups of scientists that have gotten together to advise the telescope, the telescope project itself, on how they should use it to get the most discoveries out of it. So I lead something called the Transients and Variable Stars Science Collaboration. It's a group of about 100 people, and they're the kinds of people, the scientists now, who study some of the examples of those events in space that happen, things like flaring solar-like stars, things like supernovae, things like tidal disruption flares. There are representatives of all of those different fields in my group. And what we do is we talk about how when new decisions on how to make the telescope work or how to use it get made, we say, well, that would be good for this reason and bad for this reason, or, oh, we'll miss out on this really amazing discovery that we could have made if only we go back every 4 days instead of every 5 days. And so I lead that group of people. I also work on something called the Science Advisory Committee. The committees all have crazy names. But what that does is serve as a liaison between the people that are sort of embedded in working on the project and the random other astronomers that will be future users but haven't really started to think about that yet. So I try to communicate with them and find out, you know, besides my group of 100 people, what else does the rest of the community want to know? You there? I can repeat it. You should repeat it. Yeah. The question was, what made you decide on a 3-day cycle? So actually, nothing yet. So one of the things that we're doing this week, in particular today and tomorrow, is we're doing what we call the Observing Strategy Workshop, where a bunch of us have gotten together and we're studying what the difference is between doing, you know, going back to a certain patch of the sky every 3 days versus 5 days versus, you know, do you want to take one image and then come back in an hour, or does it matter if it's that or 2 hours? We're trying to figure out all of that yet right now, because we have a little while until the survey really gets going, and so we're trying to make sure that we've made the best possible choices. So we haven't decided that yet, but in part that's just driven by how quickly the telescope can move across the entire night sky, but there's some flexibility, so we're trying to figure out whether that's the best or not.
I think it's kind of a two-part, but I think they're probably related. You talk about the mirror. Just wondered, is that a segmented mirror like a Keck, or is it one solid mirror? And does that have anything to do with the other smaller telescope that's shown further down the mountain?
So in the images of the telescope where it will be kind of along the ridge of that mountain, those are actually other observatories that are independent of LSST. So that's just because usually when there's like what we call a good site, which means like a place that has good weather essentially and dry air, there are usually multiple telescopes in a particular site. So those are independent of LSST. The actual mirror itself is really just a giant monolithic piece of glass. And I think that there are even images from it being melted and spun that are up on YouTube, movies of of the glass melting, which is pretty cool to see. And so when you see that giant piece of polished glass, it's just a huge, giant piece of polished glass.
I'm not an astronomer in any stretch of imagination, but with the telescope located on a mountain in Chile, aren't you looking at just a portion of the universe?
Yeah, it's all the visible sky from Chile, but that is absolutely true. The Earth peskily gets in the way.
What are you going to do about it?
Well, the Earth is my favorite planet, so I mean, actually, even with space telescopes, if they're very close to Earth, so the Hubble, for example, orbits the Earth, and that means that the Earth gets in the way of the Hubble like half the time too. You know, it's like, but it's, you know, still a nice place to live. Down front.
So when you're deciding on where to map, like where you're going to gather the images, is it driven by algorithm or is it more of a manual kind of gathering?
Yeah, good question. So where we actually tile the night sky is all algorithm. It's all like computer robot, basically. Figuring out which parts of the sky are best to observe at that moment, and also the priority that it puts on different parts of the sky changes with time. So it's this very complex thing. And it slews, like literally it goes from one part of the sky to the other in a matter of seconds. So it's much faster than a human would be able to make decisions.
So when you say your group is working on observing strategy, does your group then form an hypothesis of any sort, and what might that hypothesis be?
Well, so usually what we do is, at the moment, one of the things we'll work on tomorrow is that there's a team of people who have made this simulation of what the observing strategy will be like. So they've made a couple of choices, almost like a menu of different flavors of observing strategy with different choices made in them. What that gives us is information on like how the sky has been observed, and we can use what we know about the various science things that we want to study, whatever it happens to be, and look at whether we do better or worse at the kinds of things we might like to do when we have the actual data. So it's not really like a formal hypothesis. You might say, well, I want to try, this particular change to the observing strategy because I feel like it will do better at X, whatever it happens to be, do better at catching a special kind of supernova. But at the moment, what we have is the sort of menu of differently flavored simulations. And so we can actually test each one of those and see which one performs. But ultimately, what we're trying to do is come to a kind of consensus, because there's only one LSST, and we have to use it in a particular way. And so to a certain extent, it's about coming together as a community and figuring out what will be the best for the maximum number of science cases. It might not be perfect for everything, but we want to do really well on all of our goals.
So I have a two-part question. I know that glass from carpentry moves, like after 100 years it will settle. My question, or the two parts, is how long do you expect that mirror to last? And if it starts to move like glass does, how often do you plan on maintaining it?
Ooh, that's a good question. So at the very least, the mirror will be on the telescope and observing for 10 years, because that's the telescope at the actual survey duration. But it, of course, will be on the telescope prior to that, so it'll be longer than 10 years. Over that time, I actually don't know how often they will be servicing it, but typically at other, for example, at other observatories, you do what's called re-illuminizing the mirror, so basically just repolishing the mirror. So I don't actually know what the servicing schedule is for LSST, but I would guess that it's the shininess of the mirror before the actual deformation of the glass that's important. But that's...
I was wondering that because the movement of the glass might affect the images, so I was just wondering.
Yeah, it most certainly, you're absolutely right that it most certainly would if it started to sag or deform. They're polished to incredibly detailed, precise shapes. But all of that, fortunately, the actual properties of the material and the way that it's polished and the way that the structure that holds it is made is tested very, very carefully prior to it being deployed. I keep wanting to say launched, but not launched. Deployed, yeah.
It does have active optics to support the structure too.
Right. There was a question down here.
So what kind of things do you personally want to observe that would lend to your interest in
So one of the things that I'm really interested in is stellar flares. So actually, since I can kind of futz around right now while I'm show. So one of the things that I'm really interested in is stellar flares, and the reason for that is that those are the kinds of things that are responsible for showering their planets with high energy radiation. I hope to one day be able to discover the place in which I put this video that I really want to show you. All right. So we'll just let this play behind me because it's videos of the sun. So some of the things that you're going to see are these amazing loops of material that are on the surface of the sun. These are part, as I said, of the magnetic activity of our star that exists also in other stars. And one of the things we've learned, the other thing that I work on is a mission called NASA's Kepler mission, which is a space telescope that looks for planets around other stars. And one of the things that we've learned is that basically planets that are the size of Earth, small rocky things, are very, very, very common. And not only are they common around stars like our sun, they're also common around stars called M dwarfs. These are just very red, small stars that are much more common than our sun. So they're 70% of all stars, essentially. Now, M dwarfs, because they're very small and very red, they don't give off, they're not intrinsically bright. They don't give off a lot of energy. And so in order for the planets that orbit them to get enough energy from the star to be kind of the right temperature where you might expect to find liquid water, or you might possibly find liquid water, they have to be very close. Those planets have to be very close to their star, almost like you're around a campfire and you're kind of like trying to huddle around the campfire to catch that energy. And that means that those planets that are around those stars are particularly vulnerable to things like that. So one of the things that I want to look for is how frequently you expect to find flares on these stars. Now you can do that already with individual stars, but one of the cool things that you can do with something like LSST is that you can see these stars out to much greater distances, and you can't study the individual like flaring events that well because they happen so quickly. But you can basically make a map of how often they happen as a function of age in the galaxy. So stars, when they're very young, they're actually more active and they flare more often, sort of like teenagers having tantrums. And then they kind of tail off with time. But these little red stars appear to always have flares to some extent or another. And so one of the things that I want to know is, okay, you know, if you survive the teenage years living with this star, is it always a big effect on the chemistry of the atmosphere of the planet? Do you always have to account for these flares, or do you just get to forget about them after a couple of billion years and be like, oh, remember when you were a teenage star and you were zapping me with X-rays all the time? Wasn't that fun? So, you know, I want to know basically like whether that is always important or not, because it affects what we think the planets around them might be like, what their actual chemistry of their atmospheres would be like, whether they have atmospheres at all. And that's something that you can do with a project like LSST, where you can see lots and lots and lots of them. So even though you can't study them individually that well, you can study kind of the statistics, the rate.
Are those real pictures? Or?
This is actual video of the sun. See, you doubted me when I said the YouTube video channel for the Solar Dynamics Observatory was cool, but it is really cool. Oh, you have the mic up there.
So are astronomers hopeful that we may find, it's a two-part question real quick. Are we hopeful that we're going to find some of the stars that are associated with the birth of our sun, the light cluster that we were formed with?
That would be, I think that would be really hard to do. So I personally don't work on that, so I don't actually know. I think it would be kind of hard to figure out what stars we were born with. The question comes from the fact that it's pretty common for stars to be born in clusters of stars. So you grow up with some group of stars. And we know how we're moving through space, but a lot of times those clusters kind of dissipate over time. And so I think it would probably be pretty challenging to figure out kind of where our home cluster would have been. But we could certainly study other clusters of stars, and we could study, for example, those clusters as a function of how old we are.
Even compositionally?
Even, sorry, say that again?
Even compositionally? Like what?
Well, the problem is that stars are, for the most part, they're made up of like hydrogen and helium, and then like a little smattering of other things that, you know, astronomers all call the smattering of other stuff metals, though it's not all metal. It's a weird cultural thing. But, you know, there are many stars that are the same sort of metallicity or the same composition as our sun, but you wouldn't necessarily then say that we were born together for that reason.
And then real quick, I asked Bob this the other night, and he threw the stick, but I failed to fetch it. My reflecting telescopes at home, I have the problem that you can't focus on Jupiter and a star cluster and a galaxy all at the same time. That was the first time I'd seen the image of the mirror. Is that the curvature of the mirror? Is that what's helping us focus on everything at the same time? Depth-wise?
Yes. Sorry, Bob? Bob has an answer.
No, but last time I saw it, had it, so.
So I'll try it again. But the mirrors, they concentrate that light from 27 feet diameter down, and then it gets down and it's nearly parallel, and I've got lots of help here, so I don't mind being wrong. And then lenses in the camera will make the rays parallel, so they're all coming in the same direction when they hit. So they're all focused. Did all the astronomers like that?
Yeah, I mean it is kind of a nifty trick to focus not just on things that are such different distances, but over such a big area of the sky is very hard to do. It's peculiar to the design of the telescope.
No, it's not. And so what they have to do is, so the mirrors bring it together, and then lenses in the camera will straighten it all out for you.
Your reflector is a parabolic mirror, and it should be. I mean, we all have a point in the sky where we consider it infinity. So I'm not sure why on your telescope you're having that problem. Bring it to my astronomy club. We'll help you out.
That's
collaboration.
When I have an eyepiece in it and I focus on Jupiter, but then I go to focus on nebula, shouldn't I be focused on?
No, you really shouldn't, because it's all at infinity. You may want to fine tune it for detail, but it shouldn't.
This is if everybody's.
Yeah, not huge amounts.
If you're interested in pursuing astronomy, this is Cliff Mygatt. He's the president of the Olympic Astronomical Society. I want more questions. I want to just add that tomorrow night, before I forget, we've got 3 more talks tomorrow night at the Pacific Planetarium. Bryce Kalmbach from the University of Washington will be talking about dark matter and dark energy, similar to what Jim talked, but in a different manner tomorrow night at the planetarium. That's at 5 o'clock. At 6 o'clock, Frosty Economou from LSST is giving a talk called Lying in the Gutter, Looking at the Stars. If it sounds like it's going to be interesting, it's going to be very interesting. It'll be spoken in Frosty, so it's going to be funny. And at 7 p.m., Yusra Al-Sayed from UW also, she's going to be talking about the brightest black holes. So it should be very fun. Those are $5 each, but that's the only talks that aren't free, but it's $5 for a planetarium, right?
One question. What is the address of the planetarium?
Oh, thank you. Is it here? Yes. 817 Pacific Avenue on Bremerton. It's the old firehouse. It's blue now.
Okay. Thank you.
Thank you. Go ahead. Sorry, Lucy.
Oh my goodness. Who actually has the mic? Oh, you have the mic. Okay. I see you both over there. What's that?
I don't need a mic.
Well, but you got to say something.
So my question is, are there any sample data sets that data geeks can play with? Even something from the other survey telescope?
Do you mean sample data sets like that are very similar to LSST?
Yes.
Well, there's some stuff that's coming soon that is from like the Dark Energy Survey and something else called Hyper Prime Cam. Those are not public yet, but they will be in the future. I think there was just recently a bunch of data by the Palomar Transient Factory that was made public, and there's also the Catalina Real-Time Survey is all public. So there are data sets that are out there. So if you really want to get shoulders deep into some data, that's one way. And if you just want to try it out, there's certainly data sets that you can work with through the tools on Zooniverse as well.
Thanks.
And then we had this young lady up here just before the back, and then this gentleman all the way in the back.
What causes solar?
So solar flares are caused by the sun's magnetic field. So the sun, kind of like a magnet that's on your fridge, has this magnetic field that goes out of one side of it, one pole, and into the other. But the sun, unlike the magnets that are on your fridge, is not a solid object. It's essentially a big ball of plasma, really gaseous. So as it spins around, it doesn't spin exactly like a basketball. It actually moves different speeds depending on what latitude you're at. So it's sort of like the equator goes around once every 25 days, and up by the poles it goes around every 30 days or so. So what happens is that that magnetic field gets tangled. So the sun ends up looking almost like a ball of yarn. If I play this again, you can kind of see this in action. This blah, 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 opening credits. Yeah, it's 2,600 terabytes, whatever. So when you see the sun here, you see these big loops. Those are big loops of tangled magnetic field. And the reason you can see them is they trap the plasma, the glowy stuff of the sun, in them, and that makes them light up. So kind of like elastic bands, each one of those loops has a certain amount of tension to it. And because the sun itself is moving around and all that material on the surface of the sun is moving, you get some of those bands snapping with time. And when they snap, they send all the stuff that is trapped in them, all this loopy stuff, not only out into space, but down onto the surface of the star where it heats up the star itself. And so it makes that part of the star get brighter for a little while. And it also sends material flying out into space, which you'll see momentarily. So this kind of stuff is actual like parts of the sun. It's not, you know, like giant chunks of it or anything, but it is material that is what the sun is made up of that streams out into space, and sometimes it ends up here at Earth and makes part of our atmosphere light up in the aurora.
Could you give a size comparison of the Earth to that?
The Earth is like as big as my fist. Yeah, so there, with that previous thing, it's about this big, yeah.
What about an observing strategy of stare at a particular tile as long as you can? Do you do that rather than just these quick snapshots and move?
Yeah, we actually have talked about doing that. So most of the time that LSST operates, it'll tile over the sky and do these snapshots. But we also have these like special surveys or mini surveys that it does the rest of the time. So one of those can even be what we've all been calling in the collaboration movie mode, where we just pick part of the sky and stare. And that allows us to get down to fainter depths very fast, and we also get faster cadence or closer together observations. So yeah, that is definitely one of the things we're considering. There and there and there.
What's a typical
Oh,
time?
wait, hold on. You're 3, sorry. There's one behind you with the mic.
So you guys were talking about how this is going to be the most revolutionary thing since the Hubble telescope, and I know that a lot of the reason those images from Hubble are so good is because it's actually in space and there's no atmosphere between it and what it's looking at. So I was wondering why the decision was made to put this one on Earth and why it's still going to be more revolutionary than other observatories.
So my point wasn't that it's like more revolutionary than the Hubble. It's that it's a different way of doing astronomy. And so in some sense, it's better to think of it as being complementary to the Hubble. The Hubble was transformative for the way that we think about images, in no small part because it is in space and we could get those beautiful crisp images and observe wavelengths of light that don't reach to the atmosphere here on Earth. But we also have, in the same couple of decades that we've had the Hubble, we also have incredibly rich resources here on the ground, here on Earth, of telescopes that do complementary kinds of things. So the LSST is the flagship for ground-based or Earth-based observing for the next decade. But we also have all of these other observatories that are going to go up in space. So kind of the next successor to the Hubble is the James Webb Space Telescope, which is an infrared telescope that will live out in space. One of the neat things about having something like LSST on the ground while you have those space-based observatories is that you can use them cooperatively. So you can observe the same kinds of things and learn complementary kinds of information to get crisper images than you would be able to from the ground. So one of the chief motivations for doing something like a ground-based survey is that it's way cheaper, way cheaper than sending something to space. So you can make something that's quite a bit larger and that's capable of sweeping over the entire night sky like that for a fraction of the cost that you would be able to in space. So it's not that it's like better necessarily than a space telescope, it's just complementary to that. And then we had a question down here and a question here.
There was a little black orb on the video that was moving across. What planet was that?
That's Venus. So that was actually from the transit of Venus that happened in 2012, I guess. So every, so long, every like, what is it, like 110 years or something like that? Well, it's annoyingly slightly longer than a human lifetime. There is an opportunity to be able to see the planet Venus transit in front of our own sun. So this is an example of what we call planetary transit, which we usually use actually to detect planets around other stars. Now, that's basically the only planetary transit that we can see, where it actually looks like we can see the surface of the star and we can see like the planet itself. And so it's a very special thing for us to be able to observe. Usually what we do is we just measure how bright the star is, and it blocks some of the planet going in front of it blocks some of the light. And so we actually see the star get fainter. We don't necessarily see the planet and the star itself. So yeah, that was Venus.
You can see Mercury May 9th next year do the same thing.
Ah, cool.
Last time in your lifetime.
Do you know the time compression on those videos?
I don't off the top of my head.
Do you know what typically might be?
Usually those prominences, those loopy things, sort of stick around for days to a week or so. So it's sped up, but yeah, not by a lot in some cases. It depends on what part of the video you're looking at.
2 days ago, looking through a telescope, I saw one occur just like that on the northern hemisphere in just 5 minutes. Here to here.
Yeah.
5 minutes.
Yeah, so they can stick around, but they do actually evolve sometimes on very fast timescales. And even like when we observe other stars, we sometimes see flares happen like where interesting stuff is happening like on nanoseconds. Like so, multiple timescales are kind of happening in those images. This whole quadrant is new questions.
Yeah, I'm interested, the team that you're involved in, the process that you use to come to consensus on decisions. Do you arm wrestle and the winner, that's what you go with?
Exactly. No, we do a lot of discussing, which involves meeting over the course of many years and talking about all of this stuff. Until we test ourselves too. We don't guess. We do big simulations that allow us to quantitatively study the repercussions of our decisions, and then we talk about it some more.
I don't know about the logistics of moving such a large piece of glass from where it's made across the highways, the ocean, up to the mountain.
Very, very carefully. So in the case of the mirror being stored in that airplane hangar, it was lifted by that suction cup machine that I showed you, and then put into a giant box, which was literally put on a flatbed truck, and then trucked at like 4 in the morning through Tucson. Is that right, Canute? Yeah, 4 in the morning through Tucson. And I think eventually it goes down by air or by boat. Canute?
I don't know.
Yeah.
They said it was good flowing together.
Okay. Yeah, and then eventually gets trucked up the mountain very, very carefully. There's a lot of padding in the box.
The tunnel is just wide enough to accommodate.
Oh.
Is that by air or by boat that it made a long journey?
It'll make the long journey by air. You're welcome.
So I kind of gathered that you're looking for the standard candle type supernova.
Mm-hmm.
And they're pretty rare with the 50 or so that they're able to find before.
They're fairly common actually. So it's just a matter of being observing in a particular way to be able to see that something is changing rapidly.
And so how far back in time do you think the standard candles remain the same?
Well, I think that part of what makes them standard candles is that we hope that they remain the same throughout cosmic time, because they're not very good at being standard if they have changed over time. But that's probably a question for somebody who's more of an expert in supernovae. I think we have been basing a lot of that on them being standard throughout cosmic history.
I
I understand that the mirror will be transported without its reflective surface and will be put in a vacuum chamber at the site on the mountaintop to be illuminized. Is that correct?
I think that's correct. I think that also allows it to be re-illuminized more easily, so you don't have to transport the giant mirror.
Right. Is aluminum the preferred element because it's not that expensive? Would there be another one? Obviously, some mirrors are silver, and maybe it's just easier to put in a vacuum chamber and coat.
I mean, I'd be guessing, honestly, because I don't know why aluminum has been chosen, but probably cheap and doesn't tarnish.
Right. That must be lead into the other question. If you were in space, say on the moon, you wouldn't have oxidation or degradation maybe of the surface coating of the mirror. So the moon doesn't have the atmosphere, it wouldn't have tarnishing. Obviously, getting there would be a problem. But if we had some kind of lift system that we did there, say space elevator or whatever, we'd get it maybe in pieces that were shippable by rocket to the moon. Would the ultimate observatory be on the moon and not orbiting?
Well, you have the problem that part of the moon is pointed at the sun a fair amount of time, which would be sort of annoying. But I mean, there are reasons to consider putting observatories on the moon. The primary reason not to is just that it's really expensive. And you know, things that are sort of straightforward, like digging and stuff like that, drilling on a planet that has the gravity of Earth are more challenging on places that have low gravity, for example. It's just not an environment that we're used to working in. It doesn't mean that it will always be an environment that we're not used to working in, because we'd certainly like to go and explore some of these other planets, maybe even live on other planets at some point within our own solar system. So certainly, building an observatory on the moon would be pretty cool, I think, but very expensive. And not totally without its own issues, too. You do have to contend with like micrometeorite hits that basically garden the moon, but still you don't have to have things like oxidation.
Are there any other questions? Can we give Lucy another hand, please? That was wonderful. Thank y'all for coming.